Good morning. I'm going to continue now with part 2 of black holes. Part 1, that was black holes for beginners. Well, not quite beginners. Intermediate maybe. But I didn't introduce anything fancy. And I didn't really introduce general relativity. Everything is dead simple. I didn't need it, right? Now, I'm going to go through a little bit of the history of this particular topic. It's basically you call it thermodynamics of black holes, thermodynamics. We'll take some thermodynamics from classical thermodynamics and add some new stuff. Information, for example, will be added. Not in this talk, but in the next one. So, this is a very interesting topic. Why is it interesting? Not because of the black holes themselves. I call them dark stars. I like that word better than black holes. I don't like Wheeler's terminology for anything. Incidentally, one of the characters of this is Jacob Bekenstein, and Wheeler was his advisor. I told you, you can always interlink these people. So Jacob Bekenstein was a student of John Archibald Wheeler, and he died a couple of years ago. That's Bekenstein, I mean. So, let's see. We're talking today about the thermodynamics of black holes, and I'm keeping things as simple as possible. I'll give you some references because I want to cover there and give credit to those people. Now, I don't use the derivations that they have, which are very long in their papers and a very long analysis. I use simple ones. And you say, well, are you rigorous or not? Yeah, I'm rigorous. I think I'm more rigorous than if you used quantum field theory, because quantum field theory is still out on a limb. Except for quantum electrodynamics, which has been checked pretty well, but even quantum electrodynamics is not a proper theory of nature yet. It's heading there. Listen to Dirac. The reason is the process of renormalization is used to subtract infinities which crop up in quantum electrodynamics and any quantum field theory. Okay? So renormalizing quantum field theory is an interesting process. I will give a talk on it. Actually, I like the mathematics of it. But nature it doesn't look like it fits in properly with the way nature should be. Maybe not. Maybe it is. I don't know. So let's see what we're going to do. We're going to derive the formula for the entropy of a black hole, all right? Actually, I've been using this. If you look at back some of my examples, when I talk about information and entropy, I use black holes as an example. I'm going to go back over that stuff too, but slightly in this context, a little bit better. Now, I put the references on the board. Usually I derive everything, but there is a thing called the Fulling, Davies, Unruh. They only call it Unruh, but it should be the three of them. Temperature. That I have not been able to get a proper derivation of yet, and I may not be. I have a hand waving one, and it works. Actually, I get the proper formula, but I'm not happy with it yet. I mean, I've done that a few times. I've held back, and let's say, for example, working out the form of the Christoffel symbol, I waited until I had a proper, rigorous way of doing it. I looked at the great Tooft. Even Tooft disappointed me. He says, we choose the metric to be such. In other words, we choose the covariant derivative of the metric to be 0 in a particular coordinate system. I wasn't happy with that. So, what do we have? Black holes and entropy. Well, we go back to Jacob Bekenstein, who was from New Mexico, although he worked in Israel, in 1973. Physics Review D 2333. And he worked out a formula for the entropy of a black hole. Here are their names. Stephen Fulling, 1945 to the present, English. Paul Davies, I think University of Newcastle on Tyne, I don't know, forget. Certainly old London University guy, Paul Davies, he's still with us. And Bill Unruh died, no, he's still with us, I'm terribly sorry, 1945 to the present. Stephen Hawking is very much with us. Jacob Bekenstein passed on in 2015, was born in 1947. Somebody that we won't mention today but is coming up is Claude Shannon, who was an electrical engineer and a great mathematician. And he devised the idea of information. Entropy is a lack of information. So what's information? It's related. All right. So what are the main papers? Well, Fulling, Davies, and Unruh. Paul Davies. Quantum fields on curved space. I have to confess I'm not a very good book reader, but I do refer to them. This is a great book for getting involved initially in the quantum fields of curved space. Stephen Fulling, same topic, slightly more technical. I kind of like this book. Hawking and Ellis, The Large-Scale Structure of Space-Time. I do not like this book. There's not enough physics in it for me. It's very abstract mathematics. They worry more about the mathematical theorems and formulae, and that's Hawking's style, okay? Because of, I guess, his disability, he has to be that way. Although he's had some great ideas too. All right, so that's Jacob Bekenstein. Stephen Hawking was in the Lucasian chair in Cambridge from 1979 to into 2000 something, I can't remember. The Lucasian chair was occupied also by Isaac Newton. Bardeen, Carter and Hawking, the 4 laws of black holes, 4 laws of the thermodynamics of black holes, kind of paralleling classical thermodynamics, studying heat. I put this in because that's John Bardeen of Bardeen, Cooper and Schrieffer fame. And I think also inventing the transistor, clever guy. Stephen Fulling, I've just mentioned him. He wrote this blue book. Physics Review D10 2850 1973. Now the 4 laws of black hole physics, I can't remember what year that was in, but I'm sure you can look it up in Wikipedia. And Paul Davies, 1975, Journal of Physics, A84609, and Unruh. These 3 guys came up with the idea that an object close to a black hole, or any strongly gravitating body which is accelerating, emits radiation, okay? And that is the basis for our derivation this morning. Okay, Bill Unruh is certainly available on the web giving lectures you can listen to. All right, so I hate to take this stuff off the board and all that stuff, because if I make a mistake on the lecture, I've got to write them all again. So this is black hole thermodynamics again, black holes number 2. Now, what are the constants that we have here? We have, of course, K is 1.38 by 10 to the power of minus 23 joules per Kelvin. Boltzmann's constant. And we have the universal constant of gravitation. We have the speed of light. And we have Planck's constant. They're the main constants. Now, where do they crop up? Well, we have E equals kT. Now, our starting point will be the Davies-Fuller Unruh temperature, which says this. We have a test particle close to a gravitating mass. It experiences a temperature due to its acceleration. Where G is said to be the surface gravity. You see people using the symbol tau for surface gravity. Really, it's the acceleration due to gravity on a particular object. And that's gm over r squared as usual for any gravitating object. So these are our constants, and this is our starting point. And what are we going to do? We will derive an expression for the entropy of a black hole, and for a black hole we have the Schwarzschild radius. That's all we need to make it a black hole. Set r equals this, and r is the event horizon. So we call this the event horizon. The Schwarzschild radius, right? Now the Schwarzschild radius is about 3 kilometers for the sun. The sun shrinks to be 3 kilometers. That's its Schwarzschild radius. Light won't get out of it anymore. Well, I think gravity might not get out of it, but that's a separate idea. So that's our starting point. These are our constants. There are people. I'll clean the board now and we'll get involved with our derivation. Get your heads around that because I'm going to move it. I'll get everything off. We don't need those constants because you've got them in your heads, you've memorized them, I'm sure. You have to memorize stuff. I don't like the philosophy that has developed in American schools, that people tell people not to memorize anything. I was at a parents' meeting at my son's school. And his chemistry teacher looked to me like he'd gone IB, International Baccalaureate, a disaster. If your children are in it, get them out of it. That's all I can say. The reason is, I had to work in the public school system one time. I really needed to do something. I was getting divorced and I worked in a charter school and they were adopting the IB. What a fake. And you know, it's a way for the people who are administering IB, International Baccalaureate, to make huge amounts of money. You can have anybody that teach an IB course, so long as they learn the IB procedure, they don't have to know their topic at all. In fact, they say that up front. They say, the phrase is, the content is unimportant. So we had this chemistry teacher teaching my son chemistry in his great school, and he says, these guys don't need chemistry. They need to learn how to be a chemist. What do you mean? I sent him to school to learn so that at the end of the year for chemistry, he would be able to write chemical formula, name chemical compounds, recognize basic chemical reactions, and balance chemical equations. He's not going to be able to do any of that because he's learning how to be a chemist. So they're discovering stuff. They'll be discovering stuff for a long time. He can discover all he wants at home. But at school, I want him to learn stuff. IB is fake. Separate idea. That's politics. So, oh yeah, you have a finite lifetime. So you like to learn off people who have learned stuff already, right? So you get a leapfrog ahead. If you have to keep reinventing the wheel all your life, you won't get very far. One of the reasons humans get very civilized is because they teach their offspring, and their offspring teach more to their, and so on and so forth, and you accumulate knowledge. So that's different. So we'll begin. What do we begin with? Okay. Now I forget what that was. I'll start this. To save time, I'm not going to call it the Fulling-Davies. You know, we know Fulling and Davies came out with this first. We'll call it the en route temperature because that's what you see written down in the literature. So the en route temperature is given by this. E equals kT, so therefore then just the T is that. Now it's the temperature experienced by an accelerating object. Now, of course, to be a black hole, we need an event horizon whose radius is that. Just rearranging. Now, put in for r squared down here, put 1 over it. And I get an expression for the g. And I just simplified things. G and a g gives me 1 over g. There's a 4. Look at it. 1 over g. M, 1 over m. And a c to the 4th. So that is g. So let's substitute that into our t here. So that I can get rid of this. So that's what I got to. Now let me make sure I got that right. Looks like it. This is Boltzmann's constant. So now what? So that's the temperature. The temperature of what? The temperature of this gravitating object whose acceleration on its surface is that, or the surface gravity. Now I put in an expression for the m. Or do I need to do that? No, I just go straight to calculate the entropy now. So we need to calculate the entropy. Let you get your heads around that. Now remember what the classical definition for entropy is. ds, differential ds, is dq by dt. Now q is basically du, the change in internal energy, so it's an mc squared. Okay? And we have an expression for the t here. I'm going to put it down here, but I'm going to go up here because I need space. We've got all of this. You guys take a picture with your cell phone, whatever way you do it. So, ds. I need to substitute everything in here. Now this is going to be 1 over t. This is our t, so its reciprocal is going to be this thing inverted. So c cubed is downstairs, and 8 pi g m k is upstairs. Now we have a very interesting little thing that's coming into shape. C squared c, and 8 pi g m k. Over c. Anything else? Now I notice something. derivative with respect to m of m squared times a half is half m dm, okay? So let's see what will I do with that. Sorry, there's a 2 in there, my mistake. So now I can substitute that in here. I'll do it like this. It's the same thing, okay? All right. I don't need this line. So now we'll integrate. That's ds. And I'll integrate. To get the s. Now, of course, that gives me an s plus a constant. So, integrating this thing here gives me 8 pi gk. Integral of that is just m squared over 2. Okay, so far so good. There's a C here. I'm just setting this to be 0 because entropy being added, you can start off at any one point to begin counting your entropies. Let's see if I'm okay here. Okay, what do I do now? Okay, I need to put in for the m squared. Now recall. Using the definition of the horizon, r equals 2gm over c squared, therefore m is c squared r over 2g, and m squared is c to the fourth r squared over 4g squared. Okay, just make sure I don't make a mistake. M squared gk. Putting in for the m squared, c to the fourth r squared over 4g squared. So far so good. Doesn't look like I want the way it's coming out the way I want it. Okay, well, where's the h cross c? I have to check for the h cross c. Okay, there should be h cross here. So, there should be a h cross here, and a h cross here, and a h cross here. So we're now okay. All right, good. So therefore there's a h cross here as well, and h cross here. Okay, I caught it. So now we'll cancel some things. 4 cancels, g cancels, c cancels. Pi is not gone, the pi is still there. C cubed. Now, we're going to do some recalling. Where's my k? There's a k here. I multiplied and divided by 4. Okay, the k is here. The k is here. It's Boltzmann's constant. 4 pi r squared, c cubed, h cross g. I'm going to remind you guys, but just regard yourselves that this is an expression for the entropy of a black hole that we have derived successfully, as you will see. We have S, we have c squared, we have a k, and I can get rid of this. Now the surface area of a sphere is 4 pi r squared. It's the surface area of this sphere also. It's the surface area of this black hole, the horizon. The surface area of the horizon is 4 pi r squared. I could keep writing a subscript s there, I just don't bother. Also, I remember what this was. I've derived the Planck length expression a long time ago in a whole lecture. So therefore then, LP squared is going to be this thing minus the square root, okay? So this is LP squared. Now there's a k in here. Now, I like to regard this LP squared as the fundamental unit of area. It is, in fact, the Planck area. Now, you guys can go and check all the big references that I gave you if you want to, and you will find that this agrees exactly with the Hawking formula for a black hole. 1 second. Okay, I was just looking to make sure that my camera was working. You say, is this rigorous? It's dead rigorous. It's even more rigorous than using quantum field theory, creation and annihilation operas, or quantum fields in curved space, because I only use simple principles. When you use simple principles with your head operating clearly, and you watch out for a little bit of algebra, I nearly dropped the H cross, you don't do stuff like that. K, Boltzmann's constant, times the surface area of a black hole divided by the fundamental unit of area, which I'm going to relabel as AP. Alright? Now I'm also going to suggest that you cannot get a smaller area than the Planck area. So this guy is going to be a multiple of these ones. I'm also going to say that is a quantization condition, right? because the problem with deriving the T formula is that the form of it? The Hawking unroot, sorry, Hawking unroot temperature. Oh, by the way, the Hawking formula and the unroot temperature formula are the same. In other words, Hawking radiation is emitted at the same temperature as the unroot. It's the same thing. So this sphere, the surface of it is going to be tiled because you cannot get smaller units of area. I'm going to state this, than the Planck area. So this object here is going to be some n, right? So therefore then, we have something very interesting. It's very much like 2 pi r equals n times lambda. Go back to where I derived the fine structure constant and you'll see me using that. That's the Bohr quantization condition. I'm trying to use a Bohr-like quantization condition to derive this formula for you guys. That's what's holding me up. I use this one as a starting point. Given that we know this, we can derive this. It's the Hawking formula. Oh, it's Hawking Bekenstein, sorry. It's the Hawking Bekenstein formula for entropy. So, I think that was a great result. So I write this down. Now I also work in a different sphere. I work in W space. This W thing is dimensionless and it's only proportional to this thing. And it's getting simpler. It's going to get even simpler still because I'm going to show in a minute that this 4 factor is here. It arose naturally in my derivation, but we don't have to have that 4. A particular view of the universe is that that all you need to describe everything in the universe, or therefore everything on a black hole, is on a 2-dimensional surface. So our 2-dimensional surface can either be the 3-dimensional sphere or the 2-dimensional circle. And all we got is an n, all right? Very interesting, and there is more coming up. You never know what you're going to see on this channel.